Hey everyone, this warm-up is some example problems of what we've seen throughout the entirety of Unit 4. And so the lesson that is coming up is just a bunch of practice problems from Unit 4 to help us prepare for the unit test. And that's exactly what these two problems are about. So let's go ahead and take a look at the first one here. The first one, the words are kind of weird. It says a curve has a slope of 2/5 x to the third plus x at each point x comma y on the curve. So let's reread this. A curve has a slope of 2/5 x to the third plus x at each point on the curve. So this is saying that the slope changes according to this equation here, depending on the value of x. Well, that's exactly what calculus is all about, is determining the slope of a curve, or at least the first part of calculus, the differential part, to determine the slope on a curve. And what do we call that? We call that the derivative. So with all this funky words, all this is saying is that f prime of x or y prime is equal to 2/5 x to the third plus x. The slope of the curve is equal to this relationship for any xy value. And it's our job to figure out the equation of the curve. Now I'll tell you right now, when I throw this problem out there, a lot of students read this and they think, oh, I'm finding the equation of the tangent line. No, I'm finding the equation of the curve that has this slopes relationship. This is not a constant slope, so it's not the tangent line. It is, we're looking for the curve here. So that language is a little wonky, but try and understand what it's saying. We are looking for f of x. Well, if I'm given f prime and I'm asking for f of x, that means I have to go backwards. I have to take the antiderivative. So this is a pretty easy antiderivative to take. We're just going to reverse the power rule here. And so if you remember, reversing the power rule means that you're going to add 1 to the exponent. So we're going to get 4 here. So it's x to the fourth. And we're going to take our coefficient and we're going to divide it by the new exponent. So we're going to take 2/5 and divide it by 4. And so that turns into 2/20. Okay? And then the antiderivative of x, well, we're going to add 1 to the exponent. So that'll become x squared. And we're going to divide the coefficient by the new exponent. So the coefficient here is 1, so we're going to divide it by 2. And then, of course, we also have to add our plus c, because if you remember that a derivative is the derivative to a whole family of functions that are all related by a vertical shift. Okay? So we have to figure out what that c value is, essentially. So let me go ahead and simplify this. We end up with f of x equals 1/10 x to the fourth plus 1/2 x squared plus c. Now, we always want to check our work before we go any further to make sure we didn't make any mistakes. It is easier to take a derivative than it is to take an antiderivative. So let's just go through and make sure that this makes sense. If I take this derivative, I should get back up to what I was given. So power rule, I'm going to multiply the 4 to the front. So 4/10 is 2/5. We're going to subtract 1 from 4, so we get 3. So we do, in fact, get 2/5 x to the third. Then we use the power rule here. 1/2 times 2 is 1. And then we subtract 1 from the exponent, so we get 1 there. So we get 1x, and that's perfectly right. And then, of course, the derivative of a constant is 0, so we don't have anything there. Now, from here, it gives us a point. It says that this curve passes through the point 10, comma 1034. So this function is way up there. But from here, we're just going to plug in our x and y values to find c. So this will say 1034 equals 1/10 times 10 to the fourth plus 1/2 10 squared plus c. And then we just solve it from here for c. So 1034 equals 10 to the fourth is 100,000, 10,000. So this is 10,000 divided by 10. So that's going to be 1,000 there. And then 10 squared is 100, divided by 2 is 50. And then we'll combine those like terms. So we got 1,050 plus c. subtract the 1050, so we ultimately get c equals negative 16. So that's our c value, that's our constant value, and now we have to go back and write the function. So we'd say f of x is equal to 1/10 x to the fourth plus 1/2 x squared minus 16. And that is our function. This function has a slope that is given by this for all values of x, and this function also passes through this point. So that's our answer to number 1. Okay, for number 2, it's asking for where there is a point of inflection, or where the points of inflection, plural, are. So we are given f prime of x. F prime of x is equal to e to the 2x times 5 minus x. Now, points of inflection are the points where the function changes concavity. And as long as the derivative exists there, in other words, as long as you can draw a tangent line at that point and the function changes concavity, you have a point of inflection. Well, the derivative exists for all numbers, so we can draw a tangent line everywhere. And now we just have to figure out where there's a point of inflection. Well, points of inflection occur when the function changes concavity, which implies, according to our chart, that the second derivative changes signs. So we have to figure out where the second derivative changes signs. So we need to take the second derivative first of all. And there is a couple different methods of figuring out the second derivative here. We could have distributed this and then taken the derivative. I just like the idea of using our derivative rules just to get more and more practice out of this. So we're going to use the product rule here. The derivative of e to the 2x. Remember, the derivative of e to the anything is the same thing, e to the 2x. But then we have to apply the chain rule, so it's going to be times the derivative of 2x, so it'll be times 2. So that's the derivative of the first piece, and then times the second piece, so times 5 minus x. And then plus the derivative of the second piece. Well, the derivative of 5 minus x is just negative 1. And then times the first piece, so times e to the 2x. And then we'll go ahead and simplify this guy. So f double prime of x is equal to, and I'll distribute here. So 2 times 5 is 10, so 10 e to the 2x minus 2x e to the 2x. And then here we get minus e to the 2x. And then these are like terms, so we'll add those together. So f double prime of x is equal to 9e to the 2x minus 2x e to the 2x. And then from here we'll go ahead and factor. So we can factor out e to the 2x, and we're left with 9 minus 2x here. So there's our factored form of the second derivative. We're looking for when the second derivative changes signs in order to determine where the function changes concavity. So we're going to go ahead and find all the points that are of interest here. So we're going to set this equal to 0. Now, we're going to do the zero product property here. The first term is e to the 2x. That is never equal to 0. It's exponential. And there's no shift or anything like that. E to the anything is always positive. So we don't have to worry about that one. This one is equal to 0 when 2x equals 9. So when x equals, we'd say 4.5, I guess you can say. Okay. And then from here, we're going to do a number line for our second derivative. So f double prime of x is equal to 0 when x equals 4.5. We have no domain restriction here, so we don't have any endpoints. And then the other thing I forgot to mention, we want to make sure where do we have other points of interest. That would be where the second derivative does not exist. Well, the second derivative always exists. So our other critical points, but not critical points, because critical points are dealing with f prime, not f double prime. We're talking about when f double prime is 0, got that. When f double prime does not exist, there is no places there and no endpoints. So now we're going to determine the signs to the left and right of 4.5. So we'll plug in maybe 0 to the left here. If I plug in 0 to f double prime, this is going to be positive. I plug in 0 here, 9 minus 0 is positive. So here's positive on the left-hand side. And then to the right of 4.5, maybe 20. Why not 20? I mean, you could use 5, but we'll do 20. E to the 2 times 20, that's positive. If I plug in 20 here, 2 times 20 is 40, so 9 minus 40 is negative, so positive times a negative is a negative. And so now we can see that f double prime changes signs at x equals 4.5, and f double prime exists there, f prime exists there, which means we have a point of inflection. So we would say that f has a point of inflection, f has a point of inflection when x equals 4.5, since f double prime changes signs at that point. So I hope that those two problems helped you understand a little bit more of the concepts of Unit 4. Stick around for the next video to get some more practice with those concepts, and I'll see you again next time.